Video games are very complicated pieces of software. If you're building a game from scratch, you have to solve a really staggering number of problems before you can even get to something playable to figure out if it's fun. But luckily these days you can use a game engine that provides off-the-shelf solutions to most of those common problems, so you can just focus on building the parts of your game that are new and fun and interesting. All of these modern engines are built around this same basic workflow, where you implement the interactive elements of your game world by populating that world with game objects built out of reusable components. In this video, I'd like to examine that common design pattern and see how these three engines approach it slightly differently. And then we'll look more closely at Unreal's system of actors and components, and we'll explore a few different ways of putting everything together. So let's start with Unity. You can summarize the gist of Unity's architecture pretty simply. When you run the editor, you're presented with a scene. The scene contains a hierarchy of game objects. Each game object can have any number of components attached to it. All the cool stuff like collision, sound, rendering, etc. is handled by components. Game objects don't do anything interesting by themselves. You build them into something useful by composing different sets of components. To define custom logic, you can use the scripting API to write new behavior components, which can then be attached to game objects. If you have a configuration of game objects and components that you want to reuse, you can define a prefab and then instance that prefab around the scene. Godot has a similar approach, but with even more architectural purity. Godot has nodes which are similar to components. Instead of using a behavior component to add scripted logic, you write a script that extends a particular node type, and then you can attach it to a node. Godot does away with the idea of game objects and prefabs, and instead makes scenes hierarchically composable. Every scene has a root node, and you can instance one scene into another, so you end up with one big node graph. So Unity and Godot both have this advantage of architectural simplicity. The engine presents you with a blank slate, and once you learn a few basic concepts, you're off to the races. Unreal has a similarly straightforward system. There's just more complexity lying beneath it and more complexity built on top of it. But we can illustrate a similar example with Unreal, and it looks pretty familiar. Actors are equivalent to Unity's game objects being built up from a set of components. Any actor or component type can be extended by creating a blueprint. This gives you a means of defining specialized archetypes for your objects, a la prefabs in Unity or scenes in Godot, but it also lets you script custom logic using event graphs, which are tightly integrated with the underlying C++ interface for the type you're extending. So when it comes to building the objects in your game, all three engines follow a similar design pattern. Each system has the notion of a game world, which is the virtual environment the player occupies. The game world contains game objects. These are the entities that exist in that world. These game objects are made up of components, which are the individual building blocks that add different pieces of functionality to a game object. All three engines use composition to let you build up game objects out of components. And all three engines use inheritance to implement the different component types available by default. Let's take a closer look at the inheritance hierarchy for components in Unreal. The base component type is called ActorComponent. Actor components can be registered with an actor, they have an activation state to support the notion of being switched on or off, and they have their own lifecycle and tick functions. They're used to add data or functionality to an actor, but they don't have a transform within the scene. Movement components are one example of a component that just adds functionality. For example, if your actor represents a rocket that's been fired by a player, you can use a projectile movement component to handle movement updates. Scene component represents the specialized class of components that have a spatial representation in the game world. Scene components can be attached to each other to form parent-child relationships. They have properties defining their transform relative to their parent, as well as a set of functions for getting or updating their transform in various ways. Scene component also supports the notion of component velocity, and scene components can be visible or hidden. If an actor wants to have a transform within the game world, it does so by having a root scene component assigned to it. You can use raw scene components to define local transforms within your actor. For example, if you have a mesh that needs to rotate around a specific pivot point, you can create a scene component at that pivot point, parent the mesh component to it, and then rotate the parent scene component. Examples of scene components include audio component, which plays a sound at a specific location, or camera component, which defines a particular point of view. And then there's primitive component, which is a further specialization representing all the scene components that can be rendered in the viewport and collided against. That includes mesh components, basic collision primitives, and lots of other things. Primitives have properties that define how they interact in collision checks against other primitives, as well as events that are fired when those collisions occur. If we follow this inheritance hierarchy back, we'll end up at Object, which is the common base class for actor components and actors, as well as most other engine types. We've seen how actors in Unreal are roughly equivalent to game objects in Unity, but there are some key differences. In Unity, a game object has an identity in that it represents some entity in the scene, and then other than that, a game object just serves as an empty vessel for components to be attached to. In Unreal, actors can have components registered to them, but they also have a mind of their own. Actors have a set of lifecycle methods that allow you to respond to key events, as well as a tick function that lets them implement their own per-frame logic. You can define a new actor type to represent some kind of object in your game world, and if there's data or functionality that's intrinsic to that type of game entity, you can add it directly to your actor type without wrapping it up in a component. In older versions of Unreal, the actor class was bigger and more monolithic. It implemented network replication, scene transforms, rendering, lighting, collision, movement physics, sound, and animation. If you wanted to make a new kind of game object, you'd add a new class into this inheritance hierarchy by extending actor or one of its subclasses, and you'd configure the underlying actor properties to make your actor render and behave the way you needed it to. Most of this actor functionality has since been refactored into component classes, starting with Unreal Engine 3. In UE4, the base actor class is comparatively lightweight, but there's still a hierarchy of subclasses that build off of the actor class through inheritance. And it is worth noting that every time you create a new actor blueprint, you are implicitly extending this inheritance hierarchy and creating a new type, even if you're just defining a simple archetype from off-the-shelf components. This might be a little jarring coming from Unity, the fact that there are two separate inheritance hierarchies at play when it comes to game objects. So in our earlier example, our player has a static mesh component and a box component, and it is in fact a kind of actor, but it's a specialized type of actor called a pawn. And as a pawn blueprint, ipso facto, it's also a specialized type of pawn called Giuseppe. So if you want to add some new functionality to your game, you can create a new component type, or you can create a new actor type. If what you're implementing is a single, reusable, self-contained thing that doesn't relate to game object identity, lean toward component. If it has to do with what a game object inherently is, or if it defines how an aggregation of components interacts as a whole, not just the parts, or if it's just a one-off thing that wouldn't be reusable in a way that would justify the added complexity, lean toward actor. Sometimes there are valid strategies either way, particularly when it comes to more abstract things like functionality. For example, let's say we wanted a simple first-person interaction system. If the player looks at an object and presses E, we want the object to be able to respond in its own unique script-driven way. The classic, it's the late 90s and we're all high on OOP approach would be to extend actor, make an interactable actor subclass with a virtual method. And then our interactive game objects could extend interactable actor instead of actor, and override that method. Then, when we're running a line trace into the viewport and we hit an actor, we can check whether that actor is an interactable actor. That's a straightforward approach, and it works, but the fact that it ties functionality to identity can lead to bottlenecks in our inheritance hierarchy. If an actor needs this functionality, it has to be an interactable actor. It can't extend from any other actor subclass. That may be fine, but if we had, say, a type of pawn that needed to be interactable, then our design would break down. We could get around that problem by defining an interface instead. Then our actors, no matter what type they were, could implement that interface and override the function. When we hit an actor in our line trace, we'd check whether that actor implements the interactable interface. To solve the problem using composition, we'd instead create an AActorComponent subclass. As an added benefit, we could add properties to that class so that our component can have its own state and its behavior can be configurable. Then our interactive game objects could have components to represent each of the interactions that we want them to support. When we hit an actor with our line trace, we'd check whether the actor has any interaction components. And a word of advice, if you're facing a design choice like this one, try to remember that performance is probably not as significant a factor as you think it is. You should try to make design decisions based on which design is the best fit for your project, not based on hunches about which approach will use the fewest CPU cycles. So actors are game objects that exist in the world, and components are individual pieces of functionality that can be registered to an actor. It's also worth pointing out that sometimes you don't need to use either. Sometimes you have some discrete functionality that you want to encapsulate into a neat little self-contained package to keep things organized, but it's not something that needs to be registered or activated or ticked. In those cases, it's perfectly reasonable to just make a custom object class. In the example we just looked at, we're running a line trace into the scene every frame. That happens in our pawn class's tick function. There are a couple of input variables that affect our trace, namely how far from the camera we want the trace to extend, and whether we want to render debug lines. And then we have an output variable, the hit result from that trace, that we want to store indefinitely. Instead of cramming those properties into the pawn class, I defined a helper object called interactionTrace that just extends UObject. As long as I make sure to use a U property to reference that object, I can create an instance at runtime using the newObject function, and that's all I need to do. You can also instantiate UObject classes as default subobjects in the constructor, just like you do for components, in which case they're loaded alongside the parent object. Putting everything related to this trace functionality into an object lets me control the default parameters for the trace and override them in default game.ini, and it keeps our pawn class from having too many additional responsibilities that turn its public interface into a hot mess. But we could have used a component class to represent the trace, or we could have foregone using a separate class entirely. It's up to you to make the choice that you feel is best for your use case. And that's sort of the takeaway here. Unreal offers you the same basic workflow for constructing game objects that you'd find in an engine like Unity. But ultimately, Unreal isn't just a user-friendly toolset, it's also a software framework that's wide open for you to leverage in whatever way suits your project. And since blueprints are built directly on top of the underlying C++ types and interfaces, it's still a good idea to make yourself familiar with basic software design principles and the overall design of the engine, even if you mostly stick to blueprints. Remember though, you can use whatever tools and engines you want. If somebody makes blanket statements about which tools you absolutely should or should not use without knowing anything about you or what you want to make, then they're saying a lot more about themselves than about the tools and technologies they're commenting on. So I hope you've found this video helpful. And if you're interested to know more about how Unreal Engine is put together and about that hierarchy of specialized actor classes that we touched on, I hope you'll subscribe and stay tuned for the next video. In that video, we'll walk through how an Unreal project gets booted up and initialized, starting from the main function and working our way through all the key gameplay classes until we get to the Begin Play event. If you'd like to get early access to that video now, or if you just want to support the work that goes into making these videos, feel free to have a look at my page on Patreon. And until next time, thanks for watching.